In this video, I want to tackle the truly classic problem of the ballistic pendulum. It's unlikely that any student can get through an introductory physics without doing the ballistic pendulum problem. There are also a nearly infinite variety of ballistic pendulum problems that you can find, but they have a couple particular characteristics. They always involve a pendulum, something that can swing back and forth, and they involve some sort of collision where the pendulum at some point hits something or something hits it. So a very classic ballistic pendulum problem would have the pendulum starts at rest, some projectile hits and embeds itself in the pendulum, which then causes the pendulum to rise to some angle theta. Or you might have the pendulum released at some angle theta, come down and hit something, and then you need to find what happens to the pendulum, what happens to the mass, or who knows what. So there's also the ballistic pendulum involves a pendulum that swings and some sort of collision. All right, so let's think about this in general. What sort of physics would we be able to apply to this problem? In particular, the conservation laws. Can we use the conservation laws to solve this problem? Well, is momentum conserved? Well, there's some sort of collision, and probably momentum's conserved there, but momentum is certainly not conserved in the swinging of the pendulum. If it's released from a height, or if it starts with some velocity and goes up to some height, the momentum is changing completely because there's the external force due to gravity, which is changing the system a lot. So the momentum's not conserved there. What about energy? Energy is conserved as the pendulum swings back and forth. Non-conservative force due to the tension doesn't do work on circular motion. It's only gravity that does work. So energy is conserved as the pendulum swings. But what about during this collision? Certainly in this example where the bullet embeds itself in the mass, that's a totally inelastic collision. Energy is not conserved. In fact, it's maximally not conserved. So energy isn't conserved there. And so maybe we're at a loss into how to use conservation laws for this problem at all. But we're not. And that is the essence of the ballistic pendulum, because what we want to do is to do stages of the problem. We can break the problem up into two unique stages. One stage where the pendulum swings, pendulum swings, and in the pendulum swinging stage, energy is conserved. And then there's a collision somewhere, sometime. And in the collision, momentum is conserved, and maybe, depending on the type of collision, then maybe energy. And so this is, in fact, the entire point, really, of the ballistic pendulum. It's trying to teach the problem-solving strategy of, in some cases where you can't apply your physics principles to the entire problem, your conservation laws to the entire problem, you can break the problem up into stages where each stage you can apply one of your conservation laws. All right, so let's see how this applies itself for a specific ballistic pendulum problem. Okay, so the problem I have in mind is I'm going to start with myself kind of a large one here, a pendulum. Has some length L, and it starts with some angle theta from the vertical. It's going to swing down, and at the bottom of its the bottom of the swing, it hits another mass that's resting on the ground. We'll call this mass 2. Our pendulum has some mass 1. It's on a massless string. It's going to hit this mass 2, which is on the ground. There may be some coefficient of friction here. And we're going to say it collides elastically collides elastically, and we want to find the height, the pendulum, let's call it angle. We want to find the angle that the pendulum goes to after the collision. And let's say, I may not solve this, but another thing that might be asked is that you need to find sort of how far the mass 2 goes. Right? It's going to have some energy after the collision, and it's going to go some distance before friction brings it to rest. Okay, so first, sort of visualization. This thing is the pendulum's going to come down. It's going to collide. Mass 2 is then going to leave with some velocity. What is this mass 1 is going to do? Well, it might rebound back. It might not. It might go through and come up the other side. I don't know. But it's going to either way, it's going to come back to some angle phi after the collision, as well as M2 is going to leave, and then due to friction it stops. Then some time later. All right. So what sort of physics applies to this problem? Well, again, we want to break this into parts. While the pendulum swings down, we know that energy is conserved because no non-conservative forces are doing work on the problem. So it's going to start at rest, it's going to swing down, at which point there's going to be a collision, an elastic collision at which momentum and energy are conserved. Momentum is not conserved in the initial stage. But during the collision then, sort of the collision, we have momentum and energy. Well, we know there's friction here, but we're going to invoke the impulse approximation and say that this collision is going to happen so fast that the friction is not going to provide a significant impulse due to the impulse of the masses on each other during the collision. So we're going to do the impulse approximation. We're going to conserve momentum and energy during the collision. But then before and after, the mass is going to swing back some direction. And we're going to say then after that energy is conserved again for the pendulum. And while mass 2, if it goes along, it now is acted on by friction, energy isn't going to be conserved, but we can calculate the work that friction does on the object and find sort of what distance is necessary to bring it to rest. Okay, so we use the work energy theorem for that part if we want to. So we have an idea of the types of physics that applies in the different stages, so let's go ahead and start. So stage 1, that's where the pendulum falls until immediately before the collision. And in this case, we know that we conserve energy. Okay, so to do this, we need a coordinate system and a zero of potential energy, which is in this case gravity. I'm going to use here our zero, essentially where the center of mass. If I represent these as point particles on their center of mass, I'll have the zero of my coordinate system have plus x up to be where that center of mass is, so that at the moment of collision, that's at the point of the zero of my coordinate system. I'm also going to have my zero of potential energy then, not knowing anything else, be at the same place as well. So given that coordinate system and given that choice of potential energy, then we know that the potential energy function is given by mgx. And so we have some initial energy, and that's equal to the mass of 1 times g times the height that the mass 1 is above our zero of potential energy, which is here. Okay, well, we have to figure out where that is. So that's this red height here. This is the distance that the object is above the zero of potential energy. Well, what is that? Well, we know that this whole distance here, that's L. And we know that this blue distance here, that's L cosine theta. That's just using trigonometry because we know this length here is also L. And so this red distance x, the height that the object is above the zero of potential energy, then is going to be L, the total length, minus L cosine theta. Okay, so this is now the height that the object starts above the zero of potential energy. So final, this is, and in this case, this is the final. Final is now the energy, and I mean final of stage 1 here, is immediately before the collision. Well, at that point, the object is here at zero of potential energy, so its potential energy is 0. It only has kinetic energy. So we'll call that V2, 1/2 mv squared. Okay, so in stage 1, we know we can relate these two together because energy is conserved. And so we have mgl 1 minus cos theta is equal to 1/2 mv squared. The m's cancel, and I end up with, I don't know if this is what I want to solve for. I'm just coming up with relationships that are convenient to look at. V squared 2 GL 1 minus cos theta. Okay. All right, so that's stage 1. Fine, and that gives me a relationship I might be able to use later. Now let's go to stage 2. So stage 2 will come over here. This is now the collision. Okay, and so in the collision now, we know is elastic. So that means we can use the formula we derived earlier for elastic collisions between two objects. But first, let's make sure we get a good picture of our collision and our coordinate system. So at the moment of the collision, the pendulum is at the lowest point, which means we have a 1D collision. It's going, I'm going to call this the positive x-axis. The pendulum is moving in the positive x direction with some velocity v. I'm going to call my pendulum mass 1, my block mass 2, and so v1 initial is equal to the v that we found from before, fine. v2 initial is equal to 0. It starts at rest. So given that, I can find v1 final. So at the moment, I can find v2 final as well. At the moment, I'm going to answer this question. I want to know what angle the pendulum goes to after the collision. So in this case, at first, I'm only interested in the final velocity of the pendulum. So given this setup where I've defined this to be my pendulum mass 1, my block mass 2, this is my x-coordinate system, I'm looking for the velocity of a 1 final. And from the equations we derived before, this is going to be m1 minus m2 over m1 plus m2, v1 initial plus 0, something times v2 initial, which is 0 because it starts at rest. All right. So this is equal to the v that that we found before. And so that I think that's interesting. We called that V. And so V1 final is equal to M1 minus M2 over M1 plus M2 times V, where V is the positive root of that relationship. It's the velocity we found for the pendulum from stage 1. Okay, so that gives us a relationship between the velocity initially of the pendulum right before the collision to the velocity of the pendulum right after the collision. So now let's move on to stage 3, which is where the pendulum goes back up. Okay, now again, this is now where we conserve energy. Energy conserved. Let's get a picture of what's going on here. So immediately after the collision, the pendulum now is at the lowest part of its swing. It's given a velocity v1f. Do we know what direction that velocity is in? We've defined v here to be a positive number given this coordinate system. And so this v1f, this final velocity, is going to be positive if the mass of 1 is greater than mass of 2, and v1f is going to be negative, less than 0, if the mass 1 is less than mass 2. What does that mean? So if the pendulum has more mass than the block, that means the final mass is going to be positive, and it's going to continue on straight after the collision. If the mass of the pendulum is less than the mass of the block, that's this condition, that means the velocity is negative on my defined coordinate system, which means that it's going to rebound. So this is m1 less than m2, and this is m1 greater than m2. And at the moment, we don't know which that is. We don't know the relative size of the masses. But I think it's important that, always check so we understand what's going on. So we have some velocity. We don't know which way it's going. It could go either, but it has some speed v given by this relationship. Okay, but either way, energy is conserved. It has some kinetic energy, which depends on the speed squared. The kinetic energy doesn't depend on the direction that it's going. So let's go ahead in stage 3 and conserve energy. So initially, using our same coordinate system, where right here, this is our 0 of potential energy, positive x in the up direction. So we start initially with kinetic energy, 1/2 mv squared, right? This, it's this v, so we'll call this v1 final squared. That's the initial kinetic energy of stage 3, immediately after the collision. So it is now going to rise, either to the left or to the right, to some final position at which it's at rest. So either whatever way it's going to go, one way or the other, it's going to go up to some angle phi. So that's length L. That's length L. And it's going to go up some distance here, x. And of course, we solved for that sort of distance before. So that height then, I'll do this x is equal to L minus L cosine phi. This is not theta, of course, it's a different angle, but we can calculate it the same way. This is now the final angle that it goes to after the collision. So the final potential energy that it has is mg, then the height above the lowest point of the swing, which is then L minus L cosine phi. So since energy is conserved, this energy is equal to this energy, and we have our masses cancel just like they did before, and our v1 final squared is equal to 2GL 1 minus cosine phi. Okay. So now we have this relationship that gives us our final angle that it goes to. That's what we want. And this relates it to its velocity immediately after the collision. Our collision here gives us a relationship to the velocity immediately after the collision with the velocity immediately before the collision. And stage 1 relates the velocity immediately before the collision to the angle at which it was released. So that gives us all the information we need to solve. So let's do it. Let's give us a green. So that's not what I wanted. Okay, it's not going to erase for me. All right, so we have this term here, 1 minus cosine phi, that contains the final angle. That's equal to this squared. That's here. So that's equal to m1 minus m2 over m1 plus m2 squared v squared. Right, that's here. Okay. Now we can substitute in for this. So this gives us 2GL 1 minus cosine phi is equal to this thing, m1 minus m2 over m1 plus m2 squared. And v squared is just equal to this, 2GL 1 minus cosine theta. So that's equal to 2GL 1 minus cosine of theta. All right, so I've now related my final angle that I want, the height after the collision, from to my initial angle, the angle at which it was released. Okay, so the GLs cancel, the 2's cancel, that they go away as well, and I'm left with this 1 minus cosine theta is equal to this thing. I can bring cosine on this side, make it positive, and then swing this whole thing to the other side, and I get cosine of phi then is equal to 1 minus this mass term, m1 minus m2 over m1 plus m2 squared times 1 minus cosine theta. All right. And so, interestingly, if I now look at this, what can I say? If as m2 or m1 goes to infinity, what happens in the limit of either mass becomes infinitely large if mass 2 is much larger than mass 1 or the other way around. In either of those cases, this mass term here goes to 1, right? In either case, you'll just, if mass 2 is much larger than mass 1, this thing becomes m2 over m2, which is 1. Well, negative m2 over m, which is, well, negative 1, right? So either these goes to negative 1, which when you square it goes to 1, and you'll get 1 minus 1 plus cosine theta. So you get cosine phi is equal to cosine theta. And if m1 goes to infinity, the same thing happens. The result is the same in each one because there are two solutions to this problem, right? If cosine phi equal to cosine theta gives you two solutions. This means that phi is equal to theta or phi is equal to negative theta, right? That is because, in general, cosine of theta is equal to cosine of negative theta. So the fact that cosine phi is equal to cosine theta gives you two solutions. Well, that comes back to this minus sign and the same thing that we saw before. If M1 is larger than M2, then the pendulum swings through. So if M1 is massively larger than M2, it just swings all the way through, and it comes up to the same angle on the other side. By the same token, if M2 is infinitely massive compared to M1, let's say there's a wall here of a large building, for an elastic collision then, M1 simply bounces back to the same height that it went to before. It went to theta. And so for an infinitely massive M2, M1 simply bounces back to its initial angle. So that's what this is saying here. Depending on which object is infinitely massive, whether it goes through or bounces back. Okay, and again, that sort of gives us the sign. This is going to be in general, even when it doesn't go to infinity, whether or not you have a positive or negative angle. You're not going to be able to tell from the difference in mass here if M1 is greater than M2 or vice versa. Once this is squared, we lose the information of the sign. However, we still have that sign ambiguity in solving for cosine of phi, because this could be a positive or a negative value. So in whatever result we get, we'll have to use the information, qualitative information that we learned before, given the relative masses, to know whether the pendulum rebounds or goes through. But this gives us a general relationship for the solution to the angle. So we've seen a lot of things in the ballistic pendulum. The main lesson here is how to take a complicated problem to which no conservation laws apply everywhere, break it up into stages where specific conservation laws do apply in each stage, and then be able to link those stages together to come up with a final solution. Also, it emphasizes the importance of your coordinate system. You always have to have a coordinate system so you can know the signs and the directions of your vectors, as well as always link back to your picture and visualization to be able to know what your final solution will give you. And here we have an ambiguity in the sign that depends on whether it's reflected or goes through, and that's known by the relative sizes of the masses.